Now we're going to look at this problem, 13-58. It says a 2 kilogram spool S fits loosely on the inclined rod for which the coefficient of static friction is 0.2. If the spool is located 0.25 meters from A, determine the minimum constant speed the spool can have so that it does not slip down the rod. So it fits loosely on the rod, has static friction. Okay, determine the constant speed so it does not slip down the rod. So we might want to make a couple of pictures just to give us an idea what's going on. So got this collar here. And they give us a little triangle 4, 3, 5. And if this is 0.25 here, then this side down here must be, again, 0.25 times 4/5, which is going to be 0.20, going to be this dimension right here. We'll probably need that eventually. And so let's maybe take a look at some of the forces on our collar. And now this is a case where, again, you might want to use that. You will have to use that normal, maybe normal, binormal idea. So let's first see what this looks like. And so this is 2 kilograms. And so since it's spinning around, say around the center, maybe like over the center, like over here somewhere, we can maybe think of this is maybe the normal direction. And this is maybe like what we might want to call the binormal direction, since it's spinning around this way. Though when we set this up, like our normal force is going to sort of be down here. And we'll have to think for a minute. Let's see, this is going to be 4, 3/5. This problem is actually kind of complicated as far as getting the geometry right and all the directions right. And like I said, because this over here, this is 4, 3, 5 here. And so we want to keep it from sliding down. So the friction is going to work in the opposite direction here. Our friction force is going to go that way. So let's see what we can do with this. Sometimes you can just sort of just start summing forces and stuff. So let's say if we sum the forces in the normal direction, MA normal. And so this force in the normal direction is going to be, so if this is kind of pointing in this direction, and you can see the way I have the normal here, so if we want to get in that direction, we have to use the 3, huh? So this is going to be like, and let's call this way positive. So again, we'll do our NC. And so this is pointing this way. To get it in the normal, we have to use 3/5. And then for our friction force here, notice our friction force is going this direction. And so to get its component in the normal direction, we'll have to use the 4 from this triangle up here. Like I said, this gets kind of messy. So it's going to be our friction force. And then to get it normal here, we have to use 4/5. And the right-hand side, we have our mass, which is told us 2 kilograms. And then, again, the normal velocity, remember, it's always velocity squared over rho. And so let's go to the next step here. This is going to remain an unknown. So we'll just have to keep that as our 3/5 NC. Then our friction force, that's all. Remember, our friction force is always going to be NC times mu. Again, this is just 2 kilograms. And then from up here, we decided our, if we're going to be spinning around this, maybe a center here. So our radius is going to be this value up here, huh? So velocity squared times our radius is 0.2, like this. So let me go to the next step here. And our mu was given as 0.2 and C 4/5. Let me just take that the kilograms off. Velocity squared 0.2, like this. Yes.
Is the radius 0.2 or 0.25?
Yes, the distance up to here is at 0.25. Now, since it's spinning about this, like this center, like say if you think of the pencil and it's kind of spinning around the center here, then its radius from that center will be this dimension up here, that 0.2. So in other words, this was actually just the distance along the rod, but then sort of the radius from the center is 0.2. And so we get this. And so the best we can do, we're going to still have 2 unknowns, and then this is going to be 0.44 NC equals V squared. So any questions on that so far? Questions at all? So good. So next thing, let's some stuff in the normal, the binormal direction. Let's go this direction here. Some of the forces in the binormal direction. And let me put MA, but actually, let's see. There's really not going to be any acceleration in that direction. And so let's see what we have. If we call up positive, so if we do that, so down we have this 2 kilograms. So minus 2, 9.81. And then now this NC, to put it in the binormal direction, we're going to have to use this right here. It's going to be 4/5. And then our friction force over here, once again, to put it in the normal direction. So again, look, our triangle, that's going to be what? This is going this way. To get it in the binormal, it's going to be 3/5, huh? So our friction force is going to be 3/5. And there's going to be no acceleration in the normal direction. And yeah, so let me just carry this down. 9.81 plus NC 4/5. And then our friction 0.2 NC 3/5 equals 0. And actually, from this one, we can actually solve for NC, can't we? So that's going to be 21.33. I guess that's going to end up being newtons. And so we can then put that into our other equation. And when we do that, we have 0.44 1.33 v squared. And when we solve for v, we end up getting 0.969 meters per second. So take a look at that to see if there's any questions on any of that. See if it all makes sense. Good?
So for the way we did this, if we were to make the direction of the centrifugal acceleration known, it would be along the normal axis, it would be going along the rod.
I'm sorry, say that again?
Would the normal acceleration, would it be pointing like along the axis?
Oh, I see. It would be along the axis.
Okay.
Yeah, that's right. Yeah, this is kind of strange the way we do it. Right, the way I defined this right here. Yes, that would be along the axis here. Yes. Now you could do it another way. Like you could sort of make it so that it was along here. Now the reason this way is maybe a little bit more natural is because it's actually rotating about this center like this. So in other words, let's see. In other words, it's not really rotating this way, but it's actually kind of rotating this way. And but it's the other way. What you could also do it the other way, but because of the way it's rotating, this might be a little bit more natural. Any other questions on that? Questions at all? Like I said, I think this problem is kind of hard, mainly for visualizing all these different directions here. I think this even though it's not real long, it seems to be one of the harder ones. Is there anything else? Anyone has any question on that? Okay, let's take a look at another one here. I'm just picking some sort of at random here, just to. Let's do the next one on that page 13.61. We're going to take a look at this problem. At the instant theta is 60 degrees, the boy's center of mass, G, is momentarily at rest. Determine his speed and the tension in each of the two supporting cords of the swing when theta is 90 degrees. The boy has a weight of 60 pounds. Neglect the size and the mass of the seat and the cords. And so let's see here. So we have this boy Center mass of G, determine the speed and the tension in each of the two supporting rods of the swing when theta is 90 degrees. Okay, let's take a look at this. And sometimes you just have to sort of start sketching things just to get an idea what's going on. And then you can kind of get a plan maybe from there. So once it's 60 degrees, so the boy's there. Of course, his weight's always going to be going downward. And once again, since it's spinning about this here, so it's going this way. So like the normal direction, and I don't know if there's a good way to show it here, it's going to be in towards, so the normal direction would be kind of like in this direction here, towards the center, I guess. And then so if this is the normal, then maybe call the other one the tangential direction, would maybe be like in this direction here. So if we look at, yeah, so it would go, so tangential would be like this maybe. So I don't know if, so like normal is this way, tangential is this way. Though they're kind of, the axis is kind of rotating this time because it's kind of moving with the boy. And so let's take a look at this then. So if we have, let's maybe sum of the forces in a tangential direction. And let me just see. So the boy, the speed, find the tension. Yeah, so we're going to end up having, so its force is going to be 60 pounds. And actually, so since this is 60 here, and it's a tangential direction, this is going to have to be cosine of 60 degrees. And then this is going to be equal to 60 divided by 32.2 A of t, like this. And so let's just verify that this would be 60 degrees here. So let's say, how could we do that? So let's say if we had made a little triangle here, then this is like 30 degrees here. And so this is like 90 here. And then this is going to be 60 here. So that'd be 30, 90, 60. And then so if this is 60 pounds, so yeah, I think that'd be 60 cos 60. Although, let's see, to start, I'm sorry, I think we're going to have to do this in general terms first. This is going to have to be just theta, the way they asked the question. Make this theta for now. So now A of t, so it's going to be theta. If this is, in other words, whatever angle this is, that's going to be the same as this. So let's make it cos theta. So 60, excuse me, the 60s are going to cancel. So it's going to be A of t is going to be 32.2 cos theta. And so we're going to have to use v dv is equal to the integral of a ds. And this is another one that's a little bit tricky because we have this in terms of theta, then we're going to have to get it in terms of ds. And now if you think of like if you're have like a small change in an angle, and let's say you have like a distance S, let's say, or yeah, let's say so D, no, excuse me, the S would be down here. So if this is S, so the change in S is going to be equal to the radius times d theta. So you could say the ds is going to be equal to, in this case, our radius is 10 d theta, like this. So we'll have to substitute. So over here, this is going to be integral 0 to v1 v dv equals our acceleration, 32.2 cos theta. And then for ds, we're going to have to use 10 d theta. And so let me just clean that up a little bit. That's going to be, so the left-hand side, we can integrate that right away. It's going to be v squared over 2, 0 to v1. And the right-hand side, that's going to be 332 when we multiply by 10. And then the integral of the cosine is going to be positive sine. And that's going to be from, the problem's asking for 60 to 90. Like this, and then sine of theta evaluated at 60 to 90. And so put these in must 0 by 2. And we put these values in over here. This is going to be 322. 1 must 0.866. And then V1 squared is going to be 9.29 feet per second. Excuse me, V will be 9.29 feet per second. Yeah, once again, that's kind of, this is a little bit hard as well, because again, we have this tangential force to be 60 times cosine of theta. We had to keep the theta in because they're asking going from 60 degrees to 90 degrees, we had just keep at just as theta. We found A of t in terms of theta. So if we want to find the velocity, remember the one equation we have that relates velocity to positions, this one right here, but we don't even have the position in terms of like s. So we had to make this substitution. ds is equal to the radius d theta, and substitute this here, integrate, and get this. So that's what we have. So if there's any questions so far, yeah, this is not a real easy problem either. Good?
Did we have to take the interval from 60 to 90, or can we just analyze the problem at when the voice says 90 degrees?
Yeah, let's see, determine the speed. I think the problem is because he's accelerating, yeah, I think that's the problem, is the fact that he's accelerating. Yeah, they're asking for the speed. Yeah, so we have to find out how he's accelerating, how much he's increased his speed going from 0 to 60. I think that's the problem. Is if his speed was constant, then we could do that. That's right. We could just analyze it at 90. But because of the fact, and maybe actually even if his acceleration was constant, we wouldn't have to integrate here either. But yeah, because even the acceleration is not constant, and then they're asking what speed he's going to be at 90. Yeah, I think we're stuck. I think we're stuck with it. That integral. It would be nice if we could eliminate that. Any other questions on that? Yeah, let me go to the next part then. Let's see. Finally, he's asking for the tension. And so force in the normal direction, put MAN. And so now this one I think we can do, this one I think we can do at the 90-degree point. So we're going to end up having, well, actually, we can just actually calculate this, can't we? So we do sum of the force in the normal direction. Fn is going to be the mass, 32.2, and then remember v squared over our rho. Fn is 60 divided by 32.2. And again, our velocity, and the velocity when it's, now that we've found the velocity, 9.29 squared, and then our radius is 10. So the force, the normal force is 16.08 pounds. Again, because it's asking for when he's at 90 degrees. So this is like 90 degrees here. He's done, but then also he has 60 pounds pulling down like this. So the tension is going to be equal to this 60 pounds plus this 16.08, which is 76.1 more or less pounds. And tension in each cord is going to be that divided by 2, around 38.04 pounds. Like that. Any questions on that? Yeah, this one really is not really too easy of a problem. So again, once from the last step, since we got the velocity, then we could analyze it at 90 degrees, put that value, not the velocity in there, put the radius in, find the normal force, and then his weight plus the normal is 76.1. Then I have, since there are two chords, so this should say in each chord, that's why we divide by 2. Any questions on any of that? Okay, let me pick one more, see if there's any less crazy ones here. Like I said, most of them aren't in these sections, not quite this bad, but though it does help to sort of go through some of the more difficult ones. And I guess let's go, let me do 1372. This is also not a bad one, but let's just go ahead and get through it, then we'll be done with this section. We're going to look at this problem, 13-72. 150-pound man lies against a cushion for which a coefficient of static friction is 0.5. If he rotates about the z-axis with a constant speed of 30 feet per second, determine the smallest angle theta of the cushion at which he will begin to slip off. Again, once again, I don't know about you, but the hardest thing for me, again, is to sort of analyze things from these different angles. So, once again, this is similar to the first one we did, where this guy's spinning around, and so he's at an angle here. There's almost very similar to one with a collar. So he's like here, and this is like his 150 pounds this way. And once again, he's spinning around this axis over here somewhere. And so once again, since he's spinning around this central axis, so maybe let's call this the axis of rotation. And now this time we're actually given the dimension out there, so there's just 8 feet. So we don't have to calculate that. And he's at an angle theta. It rotates about, determine the smallest angle at which you will begin to slip off. Okay, I think yes, let's do this. And there's friction force this time. And we're gonna have to see which direction that the friction force is gonna be working. So once again, let's go with normal in this direction and binormal in this direction. And let's see if we can put an NC here. And once again, let's see if we can figure out some angles here. So if this is theta, this is 90 degrees, then maybe like this down here is going to be 90 minus theta. Down in this corner right here is 90 minus theta. And so once again, we'll sum the forces in the binormal direction. I think when the book mentioned this, it said we're almost never going to have any acceleration in that direction. So this can automatically figure to be 0. So in any case, if we look in the B direction, if we call up positive, and so this 150 is going to be minus 150. And then this force here is going to be working in the positive direction. And let's see. So if this is 90 minus theta here, then going in the upward direction, let's see. So cosine of this angle put us in this direction. So if we want to go in the B direction, this is going to be sine. So plus NC sine 90 minus theta. And the friction force, I think the friction force is working downward. So in other words, he's going to try to slip off in this direction. So I think the friction force is going to work in this direction. Sine theta, and again, the acceleration is 0. And one thing to note here is that the sine of 90 minus theta is going to be the same thing as cosine of theta. And let's see if we can put some of this together. We can add one more thing and see cos theta, and then we can do mu times NC. Yeah, mu NC sine theta equals 0. And we're given that mu is 0.5. So let's go one more step. And we can maybe we'll bring the 150 to the other side and factor out the NC. This. So we may call this equation 1. And then we're going to sum the force in the normal direction. And once again, if we look up at our picture NC, once again, if we go, get normal, we'll go this direction for positive. If we look at our picture up here, our NC, again, to put that in the normal direction, it's going to be NC cosine this, huh? NC cos 90 minus theta. And then for our friction, if this is this direction, to get it in the normal direction, it's going to be let's see, no, yes, I'm sorry, yeah, NC, to get it that direction will be friction F cos theta equals, then our right hand side, 150 pounds, 32.2, and then our velocity squared divided by our rho. And once again, this over here is going to be the same as sine of theta. And so let's do this NC sine of theta, our friction. That's going to be our mu again times NC cos theta 150, 32.2. We know what the radius was, 8, and we're given the velocity 30 squared. And so if we work this all out, this is NC times sine theta 0.5 cos theta equals 524.07. And we'll call this equation 2. So we have equation 1 and we have equation 2. So now if we divide equation 1 by equation 2, so if we divide this by this, the NC's will cancel. So we'll divide the left-hand side and divide the right-hand side. And then these, so you get like NC cos theta 0.5 sine theta NC sine theta plus 0.5 cos theta. Then on the right-hand side, we have 150 divided by 524.07. So remember, we're allowed to do that. If we divide both sides by something that's equal, so in other words, this is equal to this, so we divide the left-hand side by this and the right-hand side by this, then we're allowed to do that. Then the reason we want to do that, the NC's will cancel. And then we get cos theta minus 0.5 sine theta plus 0.5 cos theta. Then the right-hand side, that's going to be 0.286. So now the only way to solve something with sines and cosines in them is to set this all equal to 0 and then plot it. So set that equal to 0 and then plot it on your calculator. And see what values of theta will make. In other words, put this equation into your calculator and see what value of theta will make that 0. And when I did that, I got around 47.87 degrees to make that 0. Yeah, so this problem wasn't real easy either. The one thing that we can get from this, from both all three of these problems, just kind of get an idea of how to set up the equation. That's probably the most valuable thing. See how to set up the normal components and the binormal components, and getting like the angles correct and everything.